Hello, this is Mike Kent. I'm a professor of computer information technology at San Jacinto College on the Central Campus, which is in glorious Pasadena, Texas, near Houston, Texas. This is an overview of how encryption and passwords work. So let's jump right in. So what is encryption? Well, if you look a definition up on the internet, it's the process of converting information or data into a code, especially to prevent unauthorized access. So we really have two types of encryption. We have single key encryption, symmetrical key, it's also known as, and then we have asymmetrical, which is commonly known as public key, private key. So why do we use encryption? Well, we want to store passwords. We don't want to store a password in the clear. We also want to encrypt data that is stored on a drive. Now, this could be done with NTFS encryption. It has it built into the file format for the partition, not the file format, the partition. BitLocker, which is Microsoft's entire disk drive encryption. And then I'm also going to talk about Veracrypt, which lets you create a file of arbitrary size, whatever size you want, and that becomes an encrypted container. Any files and folders that you put in there are encrypted. Now, when we transfer data over the public internet, we're going to be using HTTPS, or we're going to be creating VPNs. That's why we want to use it. We want to keep this data private where it's stored or when it's transmitted. So single key encryption, you can look it up on Wikipedia, it's pretty straightforward. The same key, the same password encrypts the data and decrypts the data. So the same key encrypts and decrypts the data. Somehow you have to get the password to the person at the other end. And that, transmitting a password to somebody for information you're trying to keep secret, now do you encrypt the password? Now you got to give them the password to the password. So that's a problem with single key, is there's no easy way, secure way to get the password to the other end. For those situations, we typically use asymmetrical keys, which is commonly known as public key, private key. So the way this works is you have one password key that encrypts the data, and then you have the only way you can decrypt the data is with another key. Okay, so you can freely give out, you can publish it on your website, you can email it and say, here is my public key. Somebody else can encrypt that data and send it to you, and then you unencrypt it with your private key. So the public key does not decrypt the data. Give it to anybody you want. No risk, no compromise. You can put it on key servers. And then the private key is what decrypts it. So you can look at an example right here. We generate a public key, private key pair, and that's beyond the scope of this PowerPoint to talk about how you do that. Then we take our clear text file and we encrypt it into our hash, our encrypted data, using the public key. Now we can transmit this gibberish across the internet. When it gets to Alice, she uses her private key, it decrypts it, and we get the original message back. So to my understanding, HTTPS and many VPNs use public key, private key. So characteristics of an encryption algorithm. You want it to be CPU and computer resource intensive. Okay, if somebody's going to try to brute force your password by trying password combination after password combination, you want it to take a lot of CPU time to take that clear text password and turn it into the encrypted hash that you would then look at to see if it's the same as the password. So the program that generates the encrypted data should take a long time. I mean, not a long time wall clock time, but a long time for CPU time. So if it takes a thousandth of a second to encrypt that hash, that clear password into a hash, then you can only take 1,000 guesses a second at the password. So that limits the attack, the brute force attack, greatly increases the time it takes to brute force. So examples of bad encryption: WEP for your wireless connection to your wireless access point. It was developed so long ago that CPUs had the speed of about 33 megahertz and didn't really have floating point abilities to speak of. Nowadays, a modern CPU can crack WEP encryption in about 15 minutes. WPA, the next step in wireless encryption, can be cracked in a few hours if you have a high-end video card. So you want to make sure you use WPA2 or the upcoming standard WPA3 for your wireless access points. So password encryption, like I said, you want it to be CPU intensive. It takes a long time, and that limits the number of guesses that people can generate per second. So how is a password used? Well, the encrypted password is stored on the hard drive in a secure area of the operating system. And even if somebody gets the encrypted password, it's not the end of the world. The user enters the password, the clear text password, into the login screen. The encryption algorithm is run on the clear text password, and it creates the encrypted password, the hash. Okay, now the hash is what's stored in the password file. So if what you just typed in, after it's run through the encryption algorithm, generates the same hash as is stored in the password file, Windows knows you typed the right password. Just remember that the clear text password is never stored on the hard drive or with the operating system. So if somebody steals a password file, what they're getting is a series of hashes. They're not getting the clear passwords. You hear about data breaches where the password data of some website was stolen. What they got was the hashes, not the passwords. Now they can attempt to brute force passwords into the hashes to see what the passwords really were for people, but that takes a lot of CPU time. So here's some examples of different phrases. No matter what the password is, no matter how it goes through, so no matter what the length of the password is, when it goes through the hash function to encrypt it, you're going to get gibberish of the same length no matter what the password is. So you can't look at the hash to get any clues about the length or type of password. Okay? It's a one-way algorithm. When you run this algorithm to take the clear text and turn it into the hash, there is no way to reverse that process to get back to the original clear text. You have to try every possible clear text password. You have to encrypt it with the hash function and see if you get the same digest, see if you get the same hash. That's how you know you found the password. So how do we crack passwords? So if you'll watch this video, it gives you a good overview of the process. This guy does a good job on his website. He talks about techniques such as brute force, dictionary attacks, rainbow table attacks, and then I've added one right here where you just, if you can get into Windows with admin rights or mount that hard drive from a third-party operating system, you can just rewrite the password file and make the password what you want. So brute force takes the possible combinations, the possible characters of a password, all the different possible combinations, and encrypts them using the hashing function. Then for each one it encrypts, it compares it to the password hash that's stored in the password file. So to do this brute force, or it it just starts typing passwords into the login screen, but that usually doesn't get you very far because most operating systems or login screens will lock you out after so many invalid attempts. So usually what you have to do for brute force is steal the password file with the hashes in it, and then you start running through every possible combination of possible clear text passwords, comparing it to what's in the password file, and then you finally find out that their password is password1234. So brute force. So if you have long random passwords, it will effectively take hundreds of years with the fastest computers or fastest thousands of computers to crack that password, unless you just get astronomically lucky. Dictionary attacks, on the other hand, assume that the user's password is a word in the dictionary. So you just simply encrypt 100,000 words and store them to the hash in the password file until you find a match. Now, most of these dictionary attacks will let you insert a digit, like the number 0 in front of the word, then the number 1 in front of the word, the 2, 3, 4, 5, 6, 7, 8, 9. And then it moves over one letter of the word. So 0 hello, 1 hello, 2 hello, go all the way up to 9. Then you say H0 hello, H1 hello. So you just move that digit all the way through the word and try all those combinations, because you're still just talking about millions of combinations of passwords based on a dictionary word versus trillions and billions and trillions of passwords. And then you might do the same thing, but try it with a 2-digit number instead. Okay, so dictionary attacks, if it's a simple password, you can attack a password that way. Rainbow table attacks basically pre-run all the clear text passwords into their hashes and store them in a file. So then we take the hash of the user's password where we don't know what their password is, and we compare it. We search the file of pre-compiled hashes until we find a match, and then we can look up the password. So searching a database for a match is millions of times faster than hashing passwords. So rainbow tables, these files can very quickly get very, very large. A rainbow table attack program called OpCrack, which attacks Windows XP and Windows 7, a 700 megabyte file is pretty much the English dictionary with 1 or 2-digit numbers anywhere in each possible word. If you're trying to go to truly random passwords of 8 characters or less, up to 8 characters in length, you might be talking about 30 or 40 gigabyte data file. So, but rainbow attacks are dramatically faster than brute force. Another technique that several programs use is to just rewrite the password file. So in the Windows registry, in the SAM part of the Windows registry, it stores the password hashes for each user. There is a pattern. You can put an entry in the SAM file that says this user has no password. So there are programs out there that will let you blank a Windows password for Windows XP and Windows 7 almost instantly. It takes longer to boot into the program than it does to do it. Now, there are some issues with this. If the hard drive is NTFS encrypted, all your file encryptions are lost because they were based on that password you just blanked. Now, if the hard drive's BitLockered, you're not going to get that far because unless you have the BitLocker key, you're not going to be able to get onto that hard drive to get to the password file. The other way you can do it is gain admin rights, because the admin can change passwords. And that's a technique that's used with Windows 10 local accounts. Encrypting data. So this is encrypting an entire data file or an entire hard drive into a hash of gibberish and the only way you can unencrypt it is with the encryption key, is with the password. So Microsoft BitLocker is a Windows product only. It lets you encrypt entire hard drives or a USB memory stick. VPN and HTTPS is used to transmit data between your web browser and a web server so it's secure. And Veracrypt lets you create a container. Say I want to create a 2 gigabyte container. I can put files in that container up to 2 gigabytes and they're all encrypted. But you decide on the size of the container when you create it. So BitLocker, Microsoft Windows only, it encrypts the entire hard drive, and the way that encryption key is stored, it's a 48-byte BitLocker key. It can be stored one of three ways: through the trusted platform module of the motherboard, which is a feature that Intel came up with that will store the encryption keys in a way that they cannot be accessed any other way than when you're trying to mount the hard drive. You can do it with a startup USB key that must be in the computer when you boot up, and then it gets the encryption key off that USB drive. Or you can have a user-supplied password, which is then used to access the BitLocker key. Now, just be aware that if you have a BitLocker encrypted hard drive and you're using a Windows 10 user account that authenticates versus the cloud, Microsoft Windows uploads your backup. It backs up your BitLocker key to the cloud so that if you were to ever lose that, there would be a way to unencrypt the hard drive. But that also means law enforcement agencies would be able to get access to it with a warrant. So VPN, HTTPS, this is really beyond the scope of this class, but they typically use public key, private key. I've linked a couple articles here in the PowerPoint that talks about that. VPNs can use symmetric keys, but I think more typically is probably public key, private key, because that eases the problem of getting the key to the other side. You can freely give out your public key, and that does not compromise your security. So Veracrypt was formerly known as TrueCrypt. It was an open source project that shut down, but since it's open source, another group took it up and called it Veracrypt. They did a security study on it to look for flaws. So with Veracrypt, it's just a program you download and install for Windows or Mac OS or Linux. And when you run it, it's going to prompt you to create a encrypted container, and you pick the size. If you want to be able to store a gigabyte of files, you say that's how big I want my encrypted container. And then you go through a wizard. It's gonna generate the random key to encrypt it, plus the password you type in needs to be good. And then you create that container. Now, once you have that container and you run Veracrypt, and the container is just a file. It can be any file on your hard drive that you want to create. You can name it as a Microsoft Word document so that when the container is not being used, it just looks like a corrupted Word file. It just looks like a big file on your hard drive. When you mount that file and type in the password, it mounts that container as a disk drive letter on your computer. And any files you save to that disk drive or drag and drop to that disk drive become encrypted. And any files you pull out and open, they're not encrypted. But anything you save inside that container is encrypted. So when you shut down Veracrypt, it's stored encrypted, and unless somebody has that can brute force that key or social engineer that key from you, they cannot get at those files. So it's a really good way of storing data on the cloud or a USB memory stick, because the memory stick is encrypted, or the file you put on the cloud is now encrypted. So overall videos and links for all of this. Password Cracking 101 is a short video. Cracking with Cain and Abel is another short video. This is an interesting website that talks about the 500 worst passwords of all time, and it's scary how many of them involve profanity. I'm not going to call that up. And then the 10,000 most common passwords of all time. Cracking hashes, this is an interesting exercise right here. Uh, if I go to this website, CrackStation, let me see if I can get to this website here real quick. And so here's the website. And if I put a hash in here, like I can go back to the PowerPoint and grab these hashes right here. I'm going to copy, go back to my web browser and paste them in. Prove I'm not a robot by clicking and then say crack hashes. It comes through and tells me that the first hash is the password @LPH4. The second hash is P $$word. The third one is bananas, and the fourth one is CrackStation. So, but you would never know that from this gibberish. Now, this free password hash cracker will also tell you what type of encryption was used. So, this is an example of taking the hash and going through hashes until we find a match between the hash we generated and this hash, and then we find out what the clear password is. So I'm sure they have pre-saved these hashes on this website server that's doing this. They are not doing this in real time. They are not hacking these hashes in real time. Just you can't do it that fast. The last thing that most websites do, and I'm just going to talk about this briefly, is if you take the password Apple and you run it through the hash algorithm, you're going to get the hash. Well, if that's all you do with a user's password, then every single person that uses the same password Apple will have the exact same hash, which greatly simplifies the efforts of somebody to reverse the hashes and break the hashes when they steal them from a website. So the best practice, what everybody does, is they add a salt to the password. So for this user, their password is Apple, but this random set of letters is added onto the end of the password before we hash it to get the hash. Now, in a database on that website, it says the user Smith has this salt. So every user has a separate salt that's added onto their password. So that way, if two people have the same password, they do not hash into the same encrypted string. So that's just, there's an article here I've linked in this PowerPoint, and you should take a look at that if you want to learn more about it. But that is a quick overview of encryption and passwords.